And this one actually is focused on, you saw the last time we had ETOP certified airplane, which means you got to fly over water all the way from the West Coast airfields to Hawaii. And this airplane is directed at what happens if you don't. This is an amphibious search and rescue airplane that we actually would like to have a whole bunch of these. And with that, I'll let you go ahead with Guardian.
All right, good afternoon, everyone. We are Aero Systems, and today we'll be going over our final design presentation, where we'll be discussing the performance enhancement and structural design for our aircraft, the ERAU. Just before we get too far into the presentation, I would just like to make note that the screen behind me is the primary screen, or screen A, and the screen off to my side right there is the secondary screen, or screen B. My name is Nicholas James, and I'm the design team lead for Guardian Aero Systems. Up here with me is Matthew Lade, Samarth Maroderi, Tristan Hieronymus, Clyde Mills, Andrew Howe, and up at the keyboard is Jacob Waitman. As a quick overview for our presentation, I'll start off by going over the project introduction and aircraft configuration for our design. We'll then proceed to discuss the model design and construction, as well as initial wind tunnel testing and data results. We'll then proceed to discuss the modifications we made to our aircraft and proceed to analyze the data from those wind tunnel tests. We'll then discuss flow visualization for our aircraft, as well as the aircraft's performance. We will then transition to a discussion about the structural analysis and cost and market analysis for our design, and then end with team administration and conclusions and recommendations. So as a quick introduction to our project, currently shown on the primary screen is a rendering of our aircraft, the Aquila, as of the end of the preliminary design phase. Shown on the secondary screen is an image of the wind tunnel model we used to verify the performance data we calculated during preliminary design. And on the table right there is our wind tunnel model painted in the Coast Guard library, which is our target market for this aircraft. As a quick outline for the overall design project, we began this design process in the aircraft preliminary design course, where we first established a design point to perform takeoff weight sensitivities for our type of aircraft. Based on these design points and sensitivities, we created a conceptual aircraft design and further refined that during the preliminary portion of the design course. We then transitioned to the aircraft detail design course, where we first started off by developing a wind tunnel test model, as well as an initial wind tunnel testing plan. We then used this model and test plan in order to perform wind tunnel testing, in order to verify the performance figures calculated in the aircraft preliminary design course. The final phase of the detailed design course involved modifying the aircraft in order to enhance its performance, as well as performing a structural analysis on the aircraft's preliminary design. The project motivation for our aircraft stems from two recent maritime disasters. The first being the sinking of the fishing vessel Alaska Ranger in 2008, in which a 47-person crew was plunged into freezing waters. The resulting rescue operation took approximately 8.5 hours to complete by the U.S. Coast Guard and resulted in 5 casualties due to exposure to freezing waters. The second key incident was the sinking of the merchant vessel Salindang IU in 2004. In this situation, one of the Coast Guard helicopters had actually been engulfed in sea spray while conducting rescue operations and had crashed, ultimately resulting in 6 casualties for the victims of the Salindang IU. Guardian Aero Systems aims to minimize the casualties from these incidents by developing an amphibious search and rescue aircraft that offers both a quick response time and higher passenger capacity than existing search and rescue aircraft in use by the U.S. Coast Guard. We also aim to improve the safety of the rescue crew by being able to land in the water and deploy a rescue vehicle, which minimizes the amount of time that rescue divers would spend in potentially freezing waters. And finally, we aim to be more cost efficient than current search and rescue aircraft by deploying fewer rescue vehicles to perform the same mission. Our request for proposal required us to develop an amphibious search and rescue aircraft that is capable of both water and landing and takeoff operations. This aircraft must be flown by 2 pilots and carry at least 2 medical personnel, 20 seated passengers, and 4 patients on litters. This aircraft also must have a surface area of at least 15,000 feet and a radius of action of at least 500 nautical miles. with a 3-hour on-station search endurance time at this radius of action requirement. An example mission profile for our aircraft is shown on the secondary screen. I'll now go over the aircraft configuration. The Aquila features a flying boat design with a planing tail. This means the majority of the displaced water volume will come from the main aircraft hull, and the planing tail provides increased aircraft stability while traveling through the water during landing and takeoff. The aircraft features a high-mounted wing with engines mounted on the wings in order to minimize the chance of water spray being ingested into the engines and to minimize the chance that water would come into contact with critical aircraft control components on the wings. The aircraft also features wing-mounted pontoons in order to increase the Aquila's stability while sitting in the water. The Aquila features an H-tail sitting on top of a riser in order to provide adequate static stability for the aircraft while in flight. And finally, the aircraft features a conventional tricycle-style landing gear arrangement, which provides increased ground visibility for the pilots while conducting ground operations. I'd like to pass the presentation on to Matthew Lake for model design and construction.
Thank you, Ted. My name is Matthew Lee, and I'm going to be going over our wind tunnel model design and construction. So the first thing we had to do when designing our wind tunnel model was to choose a scale. There are 5 criteria we're choosing a scale, and those criteria are wind tunnel blockage, wall effects, cost, structural bending, and velocity for a 40-pound loading. So the 40-pound loading comes from the pyramidal balance used in the wind tunnel, which has a maximum load of 50 pounds, but to ensure that there's no damage to this balance, it's limited to 40 pounds. So we found, after analysis of all these different criteria, that a 1 to 50 scale was ideal for our aircraft. This came out to having a 4.84% blockage, which is less than our maximum of 5%. Our wingspan was 27 inches about, which is less than the maximum of 36 inches. Our cost came out to be $544. Our entire structure with plastic parts did allow for 1/4 inch and 1/8 inch steel rods, as well as other metal substructure pieces to be placed into the plastic model. And we found that our maximum velocity for our wind tunnel would be 190 feet per second. Shown down the primary screen is a table showing all the different parameters of our full-scale Aquila to our 1 to 50 scale. And on the secondary screen is a 3-view of our 1 to 50 scale model with these parameters shown. Our model was designed to be printed using the 3D printers found in the Aero-Prescott campus AXFAB machine shop, which are Dimension SST 1200ES 3D printers. These print a maximum resolution of 0.01 inches of plastic. So the entire design was also designed to be modular to allow us to easily redesign the model. This has our wings able to be taken off and redesigned. The floats were meant to be taken off as well and be put on new wings. The vertical tails can be detached from the horizontal tail, and the horizontal tail can also be detached from the back of the aircraft. Sparse density plastic was used for all the non-load bearing parts, and the fuselage was hollowed out as much as possible. This was both done to both reduce the cost of the model and to reduce weight. Because all the plastic parts were supposed to be non-load bearing, we developed a metal substructure which can be seen in our ghost view on the secondary screen. And the metal substructure was designed to take the load from structural bending and put it into the steel parts. For the steel substructure, we used standard size pins and support rods to make manufacturing easier. We had flow-through engines on our wings to better simulate the turboprop engines that would be on our actual aircraft. Brass plates were used for our spray suppressors because because of the thinness of the spray suppressors that would have been printed well by our 3D printers. And lastly, our fuselage was epoxied together to increase the thickness of our fuselage. Shown now on the primary screen is all of our assembled plastic components. Now the secondary screen is our assembled substructure components. This is shown just to give a nice view of how everything fits together between our two different structures. Now on the main screen is an exploded view of our plastic parts. And in this view, you can see how everything fits together, as well as how our horizontal tail and vertical tails can be removed from each other and replaced and redesigned. And on the secondary screen shows a breakdown of each individual part and their plastic volume and then the cost from this volume to show how we got our final projected cost of $544 for our wind tunnel model. Shown now is an exploded view of our metal substructure. Shows our 1/4 inch and 1/8 inch steel rods that go through the wings, as well as a steel plate that goes through the horizontal tail to take the structural bending loads. Pointed out also is the aft support and the center support. These parts were the most difficult parts to manufacture because they had to be machined to fit the exact wind tunnel model using a mill, and that allowed for the structure to be almost had very little wobble in the model. We did have a couple of changes during our fabrication process. The first of which is that the 3D printed parts had a couple of defects, and this came out in the form of faceted surfaces on the gear pods and on the nose of the aircraft. So we did not anticipate that and had to end up finding those areas and smoothing them out in order to get a nice wind tunnel model. We also had to epoxy the floats on, so they were no longer removable because they were too wobbly on the model. And lastly, we had to epoxy the center support pin, making our internal structure permanently fixed to the model so we could never move it anymore. For the model finishing, the steps are listed on the secondary screen, but basically it was we had to scuff the model, apply the Bondo, sand it, then apply primer, sand again, and lastly apply spray paint to it. And on the primary screen is a picture of it after we finished sanding the primer. On the primary screen now is a picture of our finished wind tunnel model. You can note the green clay, which was used to fill all the different crevices and cracks at the joints and other areas, such as the T-nuts that held the floats on. Once we had our final wind tunnel model, we had to perform a structural verification test in order to ensure that the model would not break apart during the wind tunnel testing. As I mentioned before, we had a maximum velocity of 190 feet per second, so we calculated the amount of lift our wings would create at this velocity and the amount of lift that our horizontal tail would create at this velocity. Then multiply that lift by a factor of safety 1.2 to get a maximum wing loading of 42 pounds and a maximum horizontal tail loading of 6 pounds. To apply this load, we held the model upside down by the mounting plate that would be attached to the balance. Then we applied weights to the model at 3-pound increments at the mean area and chord of the wing and horizontal tail respectively until we reach the maximum loading of either 21 pounds on each of the wings or 3 pounds on each of the side of the horizontal tail. This can be shown on our secondary screen where you can see the testing process of the horizontal tail and the main wing. Through this testing, we found that there was no failure or permanent deflection of these parts. We had a maximum deflection of about 1 inch at the wingtips of the model, so we found that our model was strong enough to withstand 190 feet per second in the wind tunnel. And now I'm going to hand things off to Mark Marverdary to talk about our wind tunnel.
Thank you, Matt. I'm Samad Marverdary, and I'll be going over the wind tunnel test and testing equipment. We conducted wind tunnel tests to verify the performance of the aircraft. All tests were conducted at the facility on campus, and a subsonic closed return wind tunnel was used. It had a 32 by 45 inch test cross section, and is shown on the secondary screen. The arrow points out the freestyle velocity in the wind tunnel. For the testing equipment, we used the pyramidal balance shown on the secondary screen. It had a low limit of 50 pounds. For the data acquisition, we used a library code created by Dr. Trump, and it gave us both the force and moment data. I'll now go over the wind tunnel test plan for the kilo. We tested 4 main test configurations of the kilo. The first was the full aircraft to understand the performance of the whole aircraft. We then took the tail off to understand the contribution of the performance to the aircraft. We then took the wing and the tail off to understand the hull design performance of the fuselage. And the final aircraft configuration was the full aircraft with tufts for flow visualization and to trip the laundry layer to simulate turbulent flow. So on the secondary screen is the test for each configuration. We conducted an angle of attack speed from -4 to 20 degrees in 2 degree increments, and a beta speed from 0 to -10 degrees in 2 degree increments as well. Even though the calculated maximum velocity for the balance was 190 feet per second, we were constrained to a velocity of 82 feet per second during testing. This was because at the highest angle of attack tested, flutter was seen in the tail section of the aircraft, and this was at constraining velocity. From all the data obtained, we used the lift, drag, pitching moment, yawing moment, and rolling moment coefficients to analyze the performance of the aircraft. I'll now go over the wind tunnel analysis for the initial configuration of the kilo. Shown on the primary screen is the CL alpha curve for both the preliminary design result and the wind tunnel test result for each configuration tested. Please note that the data used was all tufted for analyzing performance, as simulated turbulent flow, and it was more realistic as this is what the aircraft sees in flight. The full aircraft configuration, CL-max, and the stall angle was lower than what was predicted. This could be attributed to the fact that there was interference between the nacelles and the wings, lowering the efficiency of the wings, resulting in earlier stall and a lower CL-max. And the data is also shown on the second screen. Shown now on the primary screen is the CDCL curve. As expected, the highest drag was for the full configuration of the aircraft, and the lowest drag was for the fuselage-only test configuration. We found that the drag for the full aircraft configuration was higher than the preliminary design result. A number of reasons could be thought of for the higher drag. The first reason was our CD0 was based on skin friction drag analysis only, and pressure drag due to separation was not taken into account during the preliminary design result. The second was the interference between the nacelles and the wings, which could not be quantified, which gave us extra drag. And the third reason was the flow through the nacelles. When the free stream velocity hits the nacelles, the velocity changes direction, adding an extra drag component. Due to all these reasons, we figured that the wind tunnel testing drag was higher than the preliminary design result. For the pitching moment analysis, as seen from the primary screen, it was seen that the full aircraft pitching moment was stable and was higher than what was initially predicted. It was also seen that the fuselage and the wings did not contribute much in stabilizing the aircraft in pitch, and the horizontal tail played the most important role for stabilizing the aircraft in pitch. The full aircraft static margin calculated was 0.34, which was higher than what was initially estimated in preliminary design. For the yawing moment analysis, the full aircraft yawing moment again followed the same trend of the preliminary design result, but the magnitude was higher. It can be seen that the fuselage had a slight destabilizing effect on the yawing moment, but the wings with no dihedral and negligible sweep had almost no effect on the yawing moment. The vertical tails again played the most important role in stabilizing the aircraft in yaw. The full aircraft configuration had a CM beta of 0.0034 per degree. For the rolling moment from the preliminary design, it was estimated that the aircraft would be completely stable. However, from the wind tunnel result, it was seen that all aircrafts were either unstable or almost had no effect from the rolling moment. And finally, in comparison, we found that the static margin and the yawing moment was stable and was higher than what was initially predicted, but the rolling moment was unstable from the initial test of the wind tunnel and was contrary to the preliminary design result. And now I'll hand over to Tristan for modifications and retests.
Thank you, Samarth. My name is Tristan Hieronymus, and I'll be going over our model modifications and our retests. Based on our initial results from our wind tunnel testing, we knew that we had to make modifications to improve the performance of our aircraft. These proposed modifications are shown on the primary screen behind me. These proposed modifications were designed to do one of three things. The first thing that we wanted to do was to lower our CD0. Lowering our CD0 would allow us to fly faster, lowering our CD0 would improve our LOPD as well as allow us to fly faster, which would improve the range of the aircraft. We also wanted to increase the LOPD by either increasing the CL max or reducing drag, especially at high angles of attack, also allowing us to increase our range. Finally, we wanted to reduce our yawing and pitching moment coefficients. We found these to be very stable during our initial configuration tests. Reducing these would ensure that this aircraft was maneuverable, especially during the search phase of flight. Two of these modifications were approved for our aircraft. The first of these was a modification to the geometry of the vertical tail. The vertical tails were reduced in size by 25%, as well as changed to be asymmetric. The asymmetry was added to the vertical tails to increase their clearance to the water during water operations. Also, winglets were added to the main wings. The primary reason to add winglets to the main wings was to increase our CL max, as well as reduce drag at higher angles of attack to increase our LOPD, therefore increasing our range. The total cost of these modifications for reprinting was $370. Based on this, we were able to find a total cost of our model of $897, which is below the $1,000 budget. After these parts were printed and finished, it was necessary to retest multiple configurations to see how they affected our model design. 3 configurations were tested. These included the original wing with the modified tail, a fully modified configuration with the modified wing and modified tail, and then the modified wing with the original tail. Please note that all of these configurations were tufted, unlike the initial model testing. Aside from that, all of our test procedures were identical between our initial tests and our modified tests. I'll now go over a comparison between our initial data and our modified data. Shown on the primary screen is a lift curve slope that compares our 3 modified configurations with the preliminary design result. It was found that our fully modified configuration gave a higher CL max, as well as reduced our yawing moment, as was expected. Because of this, we decided to use a fully modified configuration to compare to our initial configuration data. Shown now is the plot of the fully modified configuration compared to the initial configuration data. It was found that the fully modified configuration with winglets did show a shift in the CL alpha curve up a very slight amount, as well as increased the CL max. The CL max was increased from 0.9 up to 1.05 with the winglets. However, a much sharper stall was seen. Because our changes were limited, we were not able to change anything that allowed us to reduce our CD knot. Because of this, on the primary screen, you can see that our drag, our CL versus CD plots for both our modified and initial configurations are very similar. However, at higher angles of attack, the winglets did reduce the drag that we saw. No changes were made to the aerodynamic center of the aircraft or the sizing of the horizontal tail. Because of this, there was no change to the CM alpha, or there was very little change was seen to the CM alpha plot of the aircraft. Due to slight shifts in the CL alpha curve, we did see an increase in static margin. The initial static margin was found to be 0.34, and our modified static margin was found to be 0.36. As expected, reducing the sizes of our vertical tails did reduce our yawing moment coefficient. We reduced the yawing moment coefficient to ensure maneuverability, and this was reduced from 0.0036 per degree down to 0.0026 per degree. This is closer to the theoretical optimum of 0.001 per degree. Finally, the rolling moment coefficient is shown on the primary screen behind me. Due to the addition of winglets as well as the reduction in the vertical tail size, we did not expect to see very large changes in the rolling moment coefficient for the aircraft. We did see a slight shift from unstable rolling moment to a stable rolling moment. However, the magnitude is still very low. This change was from 0.0018 per degree to negative 0.0064 per degree. Shown now is a comparison between all of our initial data to the modified data. As I mentioned earlier, the CL max was increased from 0.91 up to 1.05. However, the CD knot was not changed. We were able to increase our L over D max from 5.02 up to 6.71. This had an effect on our maximum range and increased our radius of action from 450 nautical miles, which did not meet our requirement, up to 650 nautical miles, which is above our 500 nautical mile requirement. I will now pass the presentation on to Clint Mills for our flow visualization comparison.
Thank you, Tristan. My name is Clint Mills. I'll be comparing flows for the initial configuration and the modified configurations. Flow vis for the initial testing and the retesting was done utilizing 1-inch string tufts. These tufts were taped directly to the surface of the model. The spacing of these tufts had to be varied due to the complex surfaces such as the engine nacelles and gear pods, where the tufts had to be placed close together for better coverage. One thing to note is that the tufts do affect the aerodynamics because they battery layer transition from laminar to turbulent flow, and this is useful in obtaining the cap flow that the full-scale aircraft will see. Shown on the primary and secondary screens is the fully modified model with both the winglets and the new vertical tails. The model is at 0 degrees angle of attack and 0 degrees beta, and as you can see on both screens, all the tufts are aligned and there is no indications of flow separation. It was previously mentioned that the winglets increased our overall lift. This can be seen on the CL alpha plot on the secondary screen. On this plot, you can see that both wings with winglets and without stall at 12 degrees angle of attack. However, the winglets give us a higher CL max, but also give us a sharper stall region where the lift rapidly decreases after the stall. Also shown on the secondary screen is a diagram illustrating how flow separates from a body tapered wing. The Aquila has a taper ratio of approximately 0.5.
So flow should separate from the trailing edge from approximately 1/3 span from the root and propagate forward and outward. This trend can be seen on the primary screen in the top picture for the wing without winglets. Encircled by the red oval, we have a large area of separation, which we can see by the direction of the tufts being reversed. However, we still have some flow at the tips. Adding the winglets decreased the size of this area of separation shown by the smaller red oval, and we have a lot more flow attached to the tips, which explains the increase in lift we see on the steel alpha plat. This means that we will have better roll control at high angles of attack. Shown on the primary and secondary screens are a side view of the aircraft at high angles of attack. During the initial flow test testing, it was noticed that there was a four-body vortex indicated by the first arrow. This vortex showed up at approximately 16 degrees and is present at high angles of attack. And on the second arrow, there is a large single vortex coming off the wingtip. Because the geometry of the fuselage was not changed, we expect this vortex to also appear in the retesting for the flow test, and this is shown on the primary screen. It was also present from 16 to 20 degrees, but it was kind of more, it was difficult to capture. Shown on the primary and secondary screens are the images of the vertical tail modification. On the secondary screen is the initial vertical tail. It was noticed during the beta test from 0 degrees beta to -10 degrees beta that no flow separation was witnessed. We wanted to verify this with the new vertical tail, and as you can see on the primary screen, with the new vertical tail at -10 degrees beta, there's no separated flow. Because the aircraft has an H tail, the vertical tails also act as end plates for the horizontal tail and affect the flow over it. During initial flow test testing on the initial model, it was noticed that the horizontal tail stalled at 20 degrees angle of attack after the wing, and we wanted to ensure this was true for the new vertical tail modification, and this is shown on the primary screen. This modification also stalled, had the horizontal tail stall at 20 degrees angle of attack, which is after the wing. So we were able to maintain pitch authority up to 20 degrees angle of attack. Previous mentioned was the sharp stall characteristics. This is shown in the video on the top screen, the primary screen. In the video, the aircraft is transitioning from 12 degrees angle of attack to 14 degrees angle of attack. And as you can see, the flow in the red circles rapidly separates, and the flow across the entire wing is separated. When it returns back to 12 degrees angle of attack, however, the flow completely repatches on the tips, so we regain roll control. I'll now pass it off to Andrew Howe, who will go over the aircraft's performance.
Thank you, Claire. My name is Andrew Howe, and I'll be going over our aircraft performance. On the primary screen, you can see our power available versus power required at sea level. Due to the CD not remaining the same between our initial wind tunnel data and our modified wind tunnel data, both are represented by just one wind tunnel line. Due to the increase in CD naught from our preliminary estimates, our power required at sea level was greater than predicted. As a result of this increased required power, our maximum velocity, which was predicted to be 370 knots, is only 220 knots from the wind tunnel data. Additionally, the velocity for minimum required power, which would be the optimal velocity for doing a search phase near sea level, which was predicted to be 125 knots from our preliminary design estimates, but from the wind tunnel data it was found to be 85 knots. Now on the primary screen you can see our power available versus power required at 15,000 feet. On this plot you can see that there is plenty of excess power from our wind tunnel data. This suggests that our surface ceiling is above this altitude. Additionally, at this altitude, our maximum velocity, which was predicted in the preliminary design to be 360 knots, was found to be only 215 knots. Next, you can see our power available was required at 32,700 feet. As you can see in our preliminary design estimates, it was predicted we would have excess power at this altitude. However, from the wind tunnel data, it was found that there is no excess power, making this our absolute ceiling. Additionally, the velocity at this altitude that we fly is 145 knots. Next is our excess power plot. The black lines are lines of constant energy height. The green lines are lines of constant piece of S from our preliminary estimates, and the red lines are lines of constant piece of S from our wind tunnel data. As you can see from this plot, our absolute ceiling, which was predicted to be 39,400 feet, is actually 32,700 feet from our wind tunnel data. Additionally, our surface ceiling, which was predicted to be 38,500 feet, is actually 32,000 feet. This 32,000 feet exceeds the 15,000 feet surface ceiling from our RFP. Next, I'll be going over our structural load analysis. Here you can see our structural opinion diagram. Using CFR 25, we found CFR 25 gives us a minimum load factor of -0.95 and a maximum load factor of 2.35 before gust lines are applied. Once we applied the gust lines, though, it was found that one load factor change, which was the positive load factor at our cruise velocity, it was changed from 2.35 up to a new maximum load factor of 2.42. Additionally, based on wing loading, it was found that our maximum velocity is 315 knots. Next is our lift distribution over our wing. This plot on the primary screen shows the span-wise distribution. This was calculated using a strength approximation, the maximum load factor of 2.42, and a factor safety of 1.5. And this was used. This distribution was used to calculate the loads that would be applied over each of the ribs in the wing. Overall, over both wings, the wings will need to be able to take a total load of 307,500 pounds. Now on the primary screen, you can see our span-wise distribution for our horizontal tail. This, yet again, was done using the strength approximation and the same factor safety and load factor. Using this, we also calculated the loads that would be applied on our horizontal tail for our ANSYS analysis. It was also determined that the overall load that the horizontal tail would need to take is 17,400 pounds. I will now pass it on to Jacob Waitman for a structural verification.
Thank you, Andrew. My name is Jacob Waitman, and I will be discussing the structural verification for our aircraft. Shown on the primary secondary screens are the full structural configurations of the Aquila. As indicated by the red arrows, the red box seen in the hull of the aircraft is the location of the fuel tanks. The wing structural design drawing is shown on the primary screen. The red ribs indicate the ribs that will be housing the nacelles for the engines, and they have a spacing of 30.1 inches between the ribs. The location on the wing toward the root of the wing has a rib spacing of 27.4 inches. The spacing of the ribs between the nacelles is 31.8 inches, and the spacing toward the outermost portion of the wing is 29.1 inches. These ribs will be 1 inch thick, with the spars of the wing being 3 inches thick. It's important to note that the cross-section of these spars is an I-beam cross-section, and these spars will be constructed with a carbon fiber composite, while the ribs will be constructed out of aluminum 7068. The empennage structural drawing is shown on the primary screen now. The ribs of the horizontal tail will have a spacing of 24.3 inches, with the ribs again having a thickness of 1 inch, and the spars having a thickness of 2 inches. It's important to note that the spars again have this I-beam cross-section and will be constructed of the same materials as the wing. The structural layout of the fuselage is shown on the primary screen. The frames have a spacing of 22 inches toward the forwardmost portion of the fuselage, but change slightly as when moved aft due to the complex shape of the fuselage hull. The thickness of these frames will be 3 inches, with the stringers having a thickness of 2 inches. It's important to note that the frames have an I-beam cross-section, while the stringers have a C-channel cross-section with a maximum overall width of 2 inches. A stress analysis was conducted using ANSYS on the wing. This analysis used the loading previously mentioned by Andrew. This found that a maximum loading on the wing came to 61,000 psi, as indicated by the red marker. The secondary screen shows the structural deformation of the wing with a maximum wingtip deformation of 19 inches. Stress analysis was also conducted on the horizontal tail. This was conducted on half of the horizontal tail, with the furthermost rib being half the center line of the horizontal tail. The maximum stress seen on the horizontal tail came to about 20,000 psi, as indicated by the red marker on the primary screen. The horizontal tail deformation is also shown on the secondary screen, with a maximum deformation at the tip of 2 inches. I'll now hand it off to Nick James to talk about the cost and market analysis.
Thank you, Jake. Once again, I'm Nicholas James, and I'll be going over the cost and market analysis for the Aquila. The development and production cost for the Aquila was calculated using the RAND cost estimation method, with costs adjusted for 2015 US dollars. The RAND estimation factored in a production number of aircraft produced of 20 units, as well as 2 test and evaluation aircraft, and includes a 50-year service life for all production aircraft, with an expected service of 1,200 flight hours per year. The total program cost sits at approximately $1.4 billion using the RAND cost estimation method, and the total life cycle cost sits at approximately $11.93 billion, or $10.93 billion. Currently shown on the primary screen is a mission comparison for both the existing search and rescue aircraft for the United States Coast Guard, as well as the Aquila aircraft that we are currently developing. As shown on this breakdown, the Aquila is capable of performing all missions for both of the HC-130H, which is used for search operations, as well as the MH-60J helicopter, which is used in rescue operations, with the exception of cargo transportation. Now I'll go over some team administration regarding Aero systems. Shown on the primary screen is a line graph displaying the comparison between the predicted hours for our team versus the actual hours worked. The number of predicted hours is based on the ratio of 2 hours worked outside of class for every hour worked inside of class. And as this point in the week, Guardian Aero Systems currently sits at approximately 130 hours above the predicted number. Shown on the primary screen is a percentage breakdown of the labor hours worked today. As shown, a majority of the tasks performed this semester have been based in either engineering or administration, and this is due to the amount of time spent either fabricating our model, performing data analysis, or logging data and preparing presentations and documentation. A further cost breakdown is now shown on the primary screen. Here it is shown that engineering tasks are by far the most expensive out of all tasks performed, and this is due to the combination of the high number of hours of engineering tasks performed, in addition to the high cost of engineering tasks. Now shown on the primary screen is the milestone chart for Guardian Aero Systems for this design phase. As can be seen here, a majority of this phase has been spent with 2 separate teams working on either the wind tunnel data analysis or the structural analysis for our design, with both teams coming together at the end in order to prepare the final presentation and perform final documentation for our design. I'll now go over the conclusions and recommendations. Our first conclusion is that the wind tunnel model we developed was completed both on time and under the total allowed budget set at the beginning of the semester. Additionally, we conclude that the wind tunnel results for both the initial test and the modified configuration showed both a lower lift and higher drag coefficient than what was determined in preliminary design, and this is an expected result. Another conclusion we have is that the winglets that we used on the modified design increased the max lift coefficient and delayed flow separation at the outer portion of the wings. And finally, we conclude that the structural analysis performed on the preliminary design indicates overestimation in the size of the components used in the structure. Based on these conclusions, we have 4 recommendations. The first recommendation being the final aircraft is to include both the new winglets and the modified vertical tail geometry, and that is shown in our test stand model right there. We also recommend that we proceed to reduce the overestimated structural components in order to save weight on the aircraft and potentially reduce the cost. We also recommend to proceed investigating possible geometry redesigns of the engine nacelles in order to further reduce the drag on the aircraft. And finally, we recommend to proceed with building a full-scale test and evaluation aircraft in order to determine real-world performance figures for our aircraft. We are Guardian Aero Systems. Thank you for your time. Are there any questions?
Top take for boundary layer control. Let's go back to 29, slide 29, please. Actually, I think it's 31. Good data plot. Okay, in this one, you made the comment to the point that for the Seal versus the Alpha, your full configuration used the tufted version of the model because it was more representative of a realistic scenario of full scale. I agree with that statement in premise. Why did you not have maybe some kind of boundary layer control comparison for the tail off and fuselage sections to compare in this figure? And then the second piece of that is why didn't you do the same thing for the drag and moment curves?
I'm going to pass this question on to Samar.
So your question is why did we compare tufted data for the tail off and fuselage? Is that correct?
That's the first part of it.
Right. So when we did the testing, as I mentioned in the configurations, we did the tufted only for the full aircraft. We did not do the test for the tail off and the just the fuselage only. So we didn't have data for it.
So my question there is why, though? If you're going to make a comparison here versus for a tufted version versus a non-tufted version, you've got a non-apples to apples comparison. What was the thought there?
I guess it's just
to that point, the logic behind it was pretty good. However, Tufts as a manner of boundary layer control for test methods in the tunnel is not really the best way to do it. There are manners of boundary layer control that should be used in place. Trip dots, gravel strips, sand, dirt, glass. There's all kinds of different options. The Barlow Ray Code book does a pretty good job of outlining those boundary layer control methods, including sizing and placement. And so the fact that you even gave it some consideration, I'm really happy with. Look at the different method the next time. Next question, slide the drag. Slide next one down. This one isn't necessarily related to boundary layer control, but did you guys do or look at any Reynolds number correcting from model to full scale?
No, we did not. I guess we could match by the house number, we would have gotten closer to a theoretical service or but no, we did not match.
It would help this picture. If you look at that, it's going some of the drag extrapolation methods for post-processing. I don't know, what was your Reynolds number in top for a model of this scale?
Just over 100.
What is your expected full scale during a cruise flight regime?
Like 70.
So if you correct for that difference, it'll collapse these curves relatively well, which will help explain some of that. Good job.
I just had a question on how you selected the tail type and what went into that.
I'll pass that question on to Tristan.
Well, the tail type was selected at the very beginning of preliminary design. We knew the biggest reason for the H-tail was because we thought initially that we needed very large vertical surfaces. If you look at the side profile of our aircraft, you'll see that it's fairly forward biased and very large. So we expected that to be a very large contributor, especially to our yawing moment. However, from the wind tunnel, we saw that it really wasn't, and that was part of the factor of reducing our tail size. But initially, we thought that we needed larger sizes for stability, pitching authority, as well as the yawing stability.
Okay. On one of these slides, you have the cost-benefit analysis sort of between the Aquila and then you have like a PAPOC and the C-130. And what would have been nice maybe is to have a breakdown of the cost for each one of those platforms. One of the things that struck me is that a lot of times in these rescues, you have really terrible service conditions. And so I'm wondering how this would handle landing in, or what sort of swell it could handle landing in.
This aircraft is designed for sea state 5 conditions. However, we are unable to test that with the amount of time we have in the semester as well as the facilities available to us. But using similar aircraft such as the Shunmei US-1A, which is currently the only aircraft that is capable of sea state 5 conditions, we designed to those geometric parameters. So sea state 5 was the target goal for our aircraft.
All right, well, great job. That's all I have.
Very nice. You guys all seem very well coordinated, and you seem like you know your stuff. You did a good job in your semester work, and it shows in your presentation. Let's see. On chart 52B, who was it presented this? You did a very nice job in explaining the differences between the flow visualization, and as a non-Aero guy, I appreciate that. You guys ended up with, you've invested 2 semesters in this design only to find out that in the wind tunnel test that the current design doesn't meet the performance requirements for the vehicle. Which I'm sure was a surprise and maybe disappointing. I have to hand it to you guys that you were very professional about how you presented those results. You didn't hide anything, you didn't try to fudge it, you didn't try to make it something that it wasn't, and my hat's off to you for the integrity that you showed in your presentation. Sometimes that's what you find out, and that is the way to do it, the way to present it. This might be more of a comment from your professor than you guys, but you're the second group that has said that your wind tunnel speed was limited by the 3D printed plastic parts. And so maybe if between your class and the other ones, you guys can capture some lessons learned about maybe how to improve the models for follow-on AE 421 classes, and so that they aren't faced with that limitation in the future. That might be useful. But nice job.
Yeah, to go on that same comment about stiffening the models, I wonder if there's something that can be done for future classes to allow you a little bit more range of experimental verification. I guess the only comment I have is when I look at the model over there with those props, we get a lot of benefit from the power flow over the wing. And I was surprised not to see that you guys take advantage of that in the conclusions and recommendations section, because I think some of the pessimism you may see in the data is going to be obviated when you blow that much air over the wing on this type of configuration. Otherwise, great job. Another very interesting design problem.
In regards to the shipping model, anyway, the tail is required to be removable so we can redesign it. Same with the wings, and that's where most of the stiffening problems comes from. You have to have it removable so you get tolerancing and clearance issues, which is what caused the flutter of our tails. So I guess if you're going about stiffening it and trying to get your velocity up higher, that's the main issue with it, is to have a removable tail requires any kind of wobbly. It makes it very difficult to do that.
Okay, any other burning questions? I know you guys who haven't presented yet are not about to ask anything. They'll ask you. Okay, guys.